Okay, so the thing we are discussing, that number of tag bit is increased in the our fully associative mapping, because in the direct mapping it is of 3 bits, but the length of the tag bit here in the fully associative mapping, this is 5 bits. So the size of the tag bit is increased. This is an one disadvantage. And another disadvantage is what? The number of comparison. The number of comparison, this is increased in our fully associative. Now, why this is increased? Because in previously direct mapping, that let's say the block number 1, this block number 1 should be present in the line number 1. This is specified, or this is fixed position issues. We can say this is fixed, that this block 1 will be present in the line number 1 only. Other than there, this block number 1 will not go. That's why we only check one comparison, that we will check that in line number 1 that particular block is present or not. CPU has to check that. But here there is no issue like that, that this block should be present in this line, another block should be present in that line. Like this concept, it is not present here. That means instead of this one comparison, which is for the direct mapping, here to check that block number 1, now this block number 1 can be present in line number 0, line number 1, line number 2, line number 3. So that means instead of checking one comparison, here we have to check what? The CPU has to check 4 lines. In this 4 line, any of where the block number 1 should be present. So instead of one comparison, here you see the comparison is what? Here 4 comparisons should be done by the CPU. So that means what? The number of comparison increases, because in that time CPU knows that if that B1 block is present in L1, then it is okay. But if it is not present in L1, that means we do not have to check other than L1, because it cannot be present in line number 2, line number 3, or line number 0. But here, if the block is not present, block 1 is not present in line number 1, then also we have to check in line number 0, line number 2, line number 3, because block 1 can be present in anywhere. So that's why here instead of one comparison, you see here the comparison is, we are doing 4 comparison. So that's why the number of comparison increases in the set associative mapping. So this is what, this is the disadvantage of the set associative mapping. Now to overcome this, we use the third step. The third, that is the, we can say, k-way set associative mapping. This is, we can say, the third type, that is the k-way set associative mapping. Now the k-way set associative mapping is the combination of direct mapping and the fully associative mapping. This is the combination of these two, the fully associative mapping and the direct mapping. The combination of these two, we use a thing, that is the k-way set associative. We name it as the k-way set associative. Now the same example we are taking, you see, we have used here the same example, that like this. So to able to discuss you that what is the disadvantage or for the advantage of this 3 mapping, that's why I have used the same example here also. The same example we have taken, that this is of this memory is 128 words, and this is what, this 128 words is divided into 32 blocks from 0 to 31, and each block can be capable of storing 4 bits, 4 words or 4 bytes. 4 bytes is capable of storing 4 bytes each block. And here also, now we say that this is the cache. This is the cache, and this cache is capable of storing 16 words, and it is capable of storing 16 words, and each line size, we say the line size equal to the block size. So line size equal to block size means line is also capable of storing 4 words, or that 4 words can present in where only in one block the 4 words can be present. So we can say that at a particular moment one block should be present in our line, and we discuss it. So we will divide that into 4 lines. So that's why 16 divided by 4. So that means 4 lines. So L0 to L3, that will be the 4 lines present. Now here, this is what, here we have used some changes. Now we have said that this K-way set associative is the combination of both direct mapping and fully associative mapping. So what we are doing here, always the way should be mentioned, the number K should be mentioned. So let's say that how many set associative present will be there. Let's say in your sometimes it is given 2-way K associative, or 3-way case, 4-way K set associative, or 8-way set associative, or 16-way set associative. So the K value should be given like this: 2, 4, 8, 16. That can be given. So we are considering 2-way K associative. The example we are taking, we are considering 2-way K associative. Now what will be the K-way set associative? This 2-way means, now this total line, we have 4 lines present. We have to divide this line that into set. In K-way set associative, we divide this into a set. Now we are considering 2-way K set associative. So that how many sets should be present in this cache? We will represent that using number of lines divided by K. We will represent this as a number of lines divided by K. So the number of lines is what? We have number of lines 4, and we are saying 2-way K set associative. So K value is what? 2. So 4 by 2. That means 4 by 2. We will here get the result as 2. Now, if we use their 4-way K set associative, 4-way set associative, in that type number of lines should be 4 and the K value should be 4. So 4 by 4, in that time it will be 1, like this. So which way should be mentioned? The K value should be mentioned. You have to find that K value, and using that K value, you have to find the number of set. The number of set we will use in the cache. So here we are taking 2-way K set associative. That's why the number of lines is what? 4, and we use K value here 2. So 4 by 2, we get the value 2. So that means in our cache, the 2 sets will be present. In our cache, there will be 2 sets present. So let's say we divide this cache memory into two sets should be present. So let's say we are considering these 2 sets as S0 and S1. This is the our 2 set we are considering, because there is 2 set, so we are considering it as the S0 and S1, these 2 sets. Now, what we have to do? We use the direct mapping formula to take the block into the cache memory. Now, which block should be present in which line? How we can do that? We can do that using the formula K mod N. We have seen that in the direct mapping. We have already seen that in the direct mapping. K mod N. We have seen this formula. Now in the fully associative mapping, we have done some changes here. Now this N is what? Specifies the line number. But that is the change in the K-way set associative. Now in set associative, this N will specify the number of set. This N will specify the number of set here. The N will specify the number of set. So we find that S0 and S1 already. So S0 is what? That means S0, line number 0 and line number 1 this will be present in set number 0, and line number 2 and line number 3, this will be present in the set number 1. We divided the line as what? Number of lines divided by k. So 4 by 2, we get the result as a 2. That means we have two sets. We have two sets, that is S0 and S1. So in S0, how many lines will be present? L0 and L1. And in S1, how many lines will be present? L2 and L3. This L2 and L3 will be present in the set number 1. And here we changes the formula, that is k mod n, and n specifies, in direct mapping, n specifies the number of lines, but here the n will specify the number of set. Here the n will specify the number of set. Now that means what? It will be k mod n. Now let's say B1 block is required. Sorry, not first block we are taking. Let's say B0 block is required. So for B0, what will be there? K value will be 0 here. For B0, we are using that block 0 should be transferred in which set. Now here we will specify, not line, that the block number will be go to which line. Here in the set associative, we will say K set associative, that this block will go to the which set is from S0 or S1, in which set this block will go. Now in the K, we are mentioning that in K we are mentioning it as a 0 because we are using the B0 here, block 0. So that's why we mentioned here as a 0. Mod n. N is what? The number of set. So how many set we have? We have two sets here. So that's why 0 mod 2. The value will get as the 0. So 0 means what? 0 means this will be go to the set number 0. Now block number 0 will be in set number 0. It is specified. But in set number 0 contains L0 and L1. This two line it contains set number 0. So it is not here. You see that it is what? This set number 0, the block number 0 will go. But the block number 0 can be present in L0 or L1. So that means what? It is specifying that in this set the block is going. But here you see that L0 and L1, between L0 and L1, any of this line, the block 0 will go. But you have to remember, this block 0 will not go to the line number 2 and line number 3. It will not go here because using the formula we find 0 mod 2, that means the value we get, that is 0. So 0 is what? 0 is present in 0 is will be, that is what? This block number 0 will be present in the set number 0 only. And inside this set number 1, we have two lines, L0 and L1. So that means between this line, between these two line, any of the line block number 0 can go. So you see there is the mixing combination of direct mapping and fully set associative mapping. Here using the formula we are specifying that which set it can go, and here also there is no restriction, that is between L0 and L1, any of the position the block number 0 can go. So this is what? This is the combination of the our fully associative. We can say this is the combination of direct mapping and the fully associative mapping. Same as that for next block. The next block is B1. Let's say the next block B1 came. Now B1 means what? This will first use the formula K mod n. We will use the formula K mod n. So K mod n, we will use what? That means here K value will be 1. This will be mod. This will be mod 2. N is what? The number of set. So 1 mod 2. That means we'll find our value 1. So 1 means what? It will be block number 1 will be present in set number 1. Block number 1 will be present in set number 1. But between this set number 1, there is line 2 and line 3. So that means block number 1 can be present in line 2 also, and present in the line 3 also. Then next, if we consider block 2, so in which set it will go? Anyone? In which set it will go if we consider the block number 2? The next block, if we consider, can anyone say? Yes, in set number 0, it will go in the set number 0. But in set number 0, we have line 1 and line 0. Two lines are present. So it is not mentioned that in but which line it will be present. But in set number 0, there is L0 and L1. And in B2 can be present in both this line. So L0 or L1, any of the position block 2 can be present. So this is the advantage that we are using both mapping techniques here. This is the advantage of that. We are using both mapping technique. So that it is why it is said that the reason of combination of direct and the fully associative mapping. Now, if we have to determine the mapping, let's say we have to determine the mapping. So the main memory physical address will be divided into two parts. Same way the physical address will be divided. We know that whatever we have seen in the direct mapping, then set associative mapping, whatever we have seen in same thing, that is, it will be divided. It will also be divided here in the memory. It will be divided into the two parts. It will be divided into two parts. That is what? That is, one is will be the offset and another one is the block number. So it will be of 5 bits. The block number will be the 5 bits, and the block offset will be the 2 bits, because at a time we can store 4 words. So 4 words means what? It will be 2 to the power 2. We can using 2 to the power 2. That means 2 bits will be used. And block number will be what? We have 32 blocks. So that means 2 to the power 5. That means our block number will be 5 bits. To represent the block number, we require 5 bits. Now this is the case of the main memory. But what will be for the cache here? In previous direct mapping, we have seen that the tag bit is of 3 bits, then 2 bits for the line number and 2 bits for the offset. In case of fully associative mapping, we have seen that 2 bits for the block offset and the 5 bits is for the tag. But here again it has some change. So what will be here? Now here the total will be 7 bits. The total will not change. The total will be 7 bits. But here first 2 bits will be for the block offset. The block offset will be same. It will be 2 bits. Now here this block number will be divided. Now divide is what? This block number will be divided into 2 parts. Now this address is for the cache. Now this block number will be divided into 2 parts. What are the 2 parts? Tag number and our set number, because here we are using the set. So it will be what? It will so it will be what? It will be our set number. So set number is what? In this set number we have 2 sets. We have seen we have 2 sets, S0 and S1. So we have 2 set, S0 and S1. So that means 2 set. We have 2 set. So to represent 2, How many bits is required to represent 2? We have required 2 to the power 1. That means it will be 2. 2 to the power 1, it will be 2. So 1 bit is required to represent. So that's why this will be 1. So this will be what? This will be 1. And our tag bit will be what? Our tag bit will be 4. So 4, 1, 2, that means tag will be 4. Our set will be what? The set size or the set here. Line number here, it will be the set number. So it will be what? It will be 1, and the total block offset will be as same. It will be of 2 bits. It will be 2 bits. So that is what. Now, when this physical address is moved into the cache memory, then we have to map that address, that is 412, like this. This will be divided. Now, tag mainly specifies that how many number of blocks, we can say how many number of blocks can be associative, or how many blocks can be mapped. So that means if we say this is our total cache, this is the cache we have, this is the cache we have, that in this cache there is what? Total 4 lines is present, and these are divided into 2 parts in 2 sets. So S0 contain L1 line, L0 and L1 line. S1 contains L2 and L3 line. This 2 it contains. So that means there will be the 4 tag bit will be present. Here also 4 tag bit will be present. Here also 4 tag bit will be present, and here also 4 tag bit should be present here. So each of this line will contain a 4 tag bit. Now this tag bit, now if CPU generated an address, CPU generates the address, and if there is the 4-bit tag, and this CPU generated address tag bit will be compared with this cache tag bit, and if they are matched, if these two are same, then it will be matched. So if two are matched, then the tag will be removed, and the particular block which CPU wanting, we can say that it is present in the our cache in this moment. So this will be go for the execution to the CPU. Now let's say CPU generates an address, let's say 0010,000. Let's say this is generated by the CPU. This address, let's say, is generated by the CPU. Now first 4 bits, we know that first 4 bits, the first 4 bits of the is used for the tag. This 00100, this is used for the tag. And after that, the next 1 bit, the next 5th bit, the 5th bit will specify in set number. The 5th bit specifies what? Set number, that it is what we have seen. This 1 bit specify the set number. So it will specify that, it will specify which set is present. So here it is 0 mentioned. That means this address is, we can say this will be on present in the set number 0, because here it is 0 mentioned. So this will be present in the set number 0. Now after that the size is 00. So that means this is 00 means our what? Word number 0, because 00 they specify the block offset, the size of the block. That means B0 block. It is searching for the 00 means it is searching, it is a block offset. So that means B0. So it is what? This B0 is present in this block. So it will now CPU generated address tag will be matched with the cache tag. And when we say that they are matched, that means cache hit occurred. And here in set number 0, the CPU will search. It will not go to the set number 1, because this set number 1, this block should be present. And what is the block number? 00. So 00 means 0. So block number 0, it is searching. So this block number 0 is present in that particular moment in the set 0. If it is present, then we can say that cache hit is occurred. The cache hit is occurred. Okay, so this is what we can say. This is if CPU generated address tag is matched with the cache tag, then we can say that the cache hit is occurred. Okay, so that's how the cache hit is, we can say that cache hit is done. And if that particular block is not present in that moment in the cache, then we can say that cache miss is occurred. And so that what we have to do, we have to move that particular block or the transfer that particular block copy from the main memory again, to the cache, and then again CPU will search, and if it is fine, then we can say that the cache hit is occurred. Okay, so this is the concept of the fully associative mapping. And k-way set associative map, sorry, it will be the concept of the k-way set associative mapping. And here it is the combination of this two mapping. So CPU, how this CPU generate this address and how we have to find that, so we have seen here. So first 4 bits with consisting of the MSB bit. So this is the MSB bit. So with considering the MSB bit, the first 4 bits will represent the tag. The first 4 bits will represent the tag, and fifth bit will specify in which set the block is present, and last 2 bits which consist of the LSB bit will specify that which block or the in the word, that word which you are searching is present in which block is present or not, that block, particular block we are searching, this will specify. Okay, so it is clear to everyone.
Yes, sir.
Okay, so anyone has other, it is of any questions from this? Anyone has any question from here? One thing I that is the direct mapping. I think that is the direct mapping concept I have left. The another technique that in the physical address which I left about that, that is the how it can be done for the direct mapping. I have missed that. That is the CPU generated address. The let's say CPU generates an address like this 0001010. So let's say CPU generates the address like this. Now, if that particular will be find in the our word, this particular word will find in the main memory, then we know that first 5 bits in main memory, if we want to find, then first 5 bits represent the block number, and the last 2 bits represent the block size. So it is mentioning that 0010. That means what? That means it is, if we convert it into the decimal, it will be 2. It will be what? It will be 2. So 2 is what? 2 means what? In the block number 2, we have to go. In the block number 2, we have to go. So in the block number 2, what are the words present in block number 2? Word 8, word 9, word 10, and word 11. And here in the last 2 bits, it is 10. It is mentioning 10. So 10 means what? 10 means also 2. That means we have to go. We have to go block number 2, and in this block number 2, what is the second word? Now if we go to the block number 2, if we go to the block number 2, then in block number 2, what is the second word? Now we always start considering from 0. So first 0th word is word number 3, 8. First the first word will be the word number 9, and second word is what? Second word of the block number 2 is word number 10. So that means CPU required word number 10 in that particular moment. In that particular moment, CPU required word number 10. So it will be the word number 10 here. Now, in the case of the cache hits and cache thing, let's say our cache in the, this is our cache memory, and this cache memory is what? This is the tag generated in our cache memory. This is our tag 010001, like this the tag are present, and 0010 in this, the line number 0 is present, 001, the line number 1 is present. And when we convert it in our cache, in cache for direct mapping, we have 3 bits for tag, 2 bits for the line number, and 2 bits for the block offset. 2 bits for the block offset. So here first we are considering it. So we have a tag number that is 010. So 010, this tag is used for the line number 0. So we are using 010. Then we have got the line number 0 we are considering. So we know that it is of 2 bits. So line 0 we are considering. That means it is 00. And at a particular moment, how many blocks should be present in the line? Only particularly one block should be present in the line at that moment. And particular block have what? Particular block have the 4 words. So that's why that means in a particular time in the line, 4 words can be present. So 4 words means we have to use the 4 combination here. So what are the 4 combination? 0001, 10, and 11. And if we do this, then that means it will, if we convert it into the decimal, it will be 32, it will be 33, it will be 34, and it will be 35. Now word number 32, word number 33, word number 34, word number 35, it is of the block number 8. So that means block number 8 will be present at that particular moment in line number 0, and its tag is 010. Same as that, if we have to find which block is present at that particular moment in the line number 1, which block is present in that time. So how we can do? There is a tag mentioned 001. So it will, the tag is 001 here. So it is mentioned, and after that line number 1. So that means 1. So we know that the line number is of 2 bits. So we have to represent this 1 using 2 bits. So we represent this 1 using 2 bits, 01. And in that particular line, how many words can be stored? Because line number and block size is equal. So that means 4 words can be present in at the particular moment in a line. So 4 combination can be present, 0001, 10 we will make, and 11. This 4 combination we will make. So for combination, if we use this 001, that means tag bit for all, and 01 for all of this line number, and it will make 20, word number 20, word number 21, 22, and 23. So it will make like that. And this word will be present where this word number 20, if we see, this is of 16, 17 for before 16, 17, 18, 19. Then 20 will be where block number 5. If we see the example, then it will be clear. So that means 14 is present in the 16 up to 16, 17, 18, 19, block 4. So that means block word number 20, 21, 22, and 23 will be present in the block number 5. So this block number 5 will be moved to the line number 1 in that particular moment, and other blocks of that range will have to stop there, or have to wait after the execution is complete for the block number 5, then they can able to acquire that line number. Okay, so that's how it is generated, and we can find the address. This particular address we find in our cache like this, checking the tag, and after that tag in which line it is present we consider, and particular moment which block is present we'll find using the combination. Okay, it is clear? समझ में आया सबको?
Yes, sir.
So this is all about our mapping techniques. Now we will, in the next class we will see about the algorithms of FIFO algorithm, then LRU, the replacement, cache replacement policies. Now we have seen the cache, the mapping. We have seen about the cache mapping. Now in the next class we will see about cache replacement policies. The cache replacement policies that is used FIFO, LRU, then other than that we will see in the next class. So then this is all about today. So thank you everyone, and in the next class we will see like tomorrow. So in tomorrow we will discuss about that. Okay, so thank you everyone. I am ending the session.
Thank you, sir.
Thank you, sir.
Okay,
Thank you, sir.
and if you required any problem, if you feel, then you can contact me. Okay, so I am ending the session.